For this problem, we're going to use something called finite differences to figure out the degree of the polynomial that best describes the data. If you were to plot these points, they would be a bunch of dots on your screen, a bunch of points. And depending on their shape, there are certain mathematical functions that would fit that shape better than others. If they're in a straight line, then we would want to have an equation of a line, or if they're nearly in a straight line. If they're more of a U shape, then we would want to use a quadratic in order to estimate or describe what it is that we would have. So if we were to take a look at the graph of these, we might be able to see what that would look like and make an estimate or a description based on that. But we don't need to graph all of those points. I wouldn't want to graph 9, 151, and these other points because they're so big and spread out. So there is an algebraic way of going through and doing that, and here's what you need to do. You need to do something called finite differences, which is what it describes up in the directions. What we want to do is take a look at our y values, and we're going to do a difference. We're going to subtract. We do the corresponding y value minus the one in front. So our x values are in order from smallest to largest. These points happen to also be, the y values happen to also be in order from smallest to largest, but that isn't always the case. The x's are, and then what we want to do is we want to go through and look at these corresponding y values and simply subtract them. So you always do a number in your y value, subtract the one right in front of it. So the first finite difference that we're going to calculate is 16 minus the number in front. So 16 minus a negative 9 is 25. And we do that with each of these y values. 26 minus 16 is 10. 41 minus 26, that's 15. 78 minus 41 is 37. And 151 minus 78 is 73. What we want to do is compare these first differences. This is the first time we went through and calculated those subtractions, so they call this our first differences. And what we want to do is look at those first differences and see if they are the same or about the same, close to each other. And if they are, then we would stop there. Those numbers are pretty spread apart, so I'm going to go through and I'm going to do the second differences. I'm going to take each one of the numbers we just calculated and I'm going to subtract them and do the same thing we did previously. So 10 minus 25 is a negative 15. 15 minus 10 is 5. 37 minus 15 is 22. And 73 minus 37 is 36. All right, so now I look at the second differences. These numbers are still pretty spread out. So I would calculate the third differences and see if those numbers are still spread out or if we can come up with something a little bit closer together. 5 minus a negative 15 would be the same as 5 plus 15, which would give me 20. 22 minus 5 is 17. And 36 minus 22 is 14. Those are pretty close together, but if we do one more difference, 17 minus 20 is negative 3. 14 minus 17 is negative 3. This row right here, that is the best row. If you were to compare all of those, this is the one where the numbers are closest together. So we have our first differences, our second differences, third differences, and fourth differences. Our fourth differences is the row that is the best. From there, we should be able to come up with the type of equation we have using this table, which is in our book. Looking at our constant finite differences, looking at numbers that are close or constant to each other, and looking, what we ended up with is our fourth differences were the ones that ended up being the best in terms of being close together. They ended up being identical. So what we would call that type of a function, a fourth degree polynomial, is called a quartic. So if your fourth difference is the one that is the same or nearly the same, you're looking at a fourth degree polynomial that would describe the data the best, which is a quartic. So for your final answer in this, you want to go through and take your differences, take a look at the numbers that you have, and the row that you have that is the same or nearly the same, that is the one that will tell you what the name of the polynomial is that best describes the data. A quartic polynomial is what would fit this data the best. That is our final answer. And the reason for that is because the fourth differences ended up being the same, and sometimes you'll just end up with values that are close instead of identical like we did here.